All right, welcome everyone. Today it's a pleasure to have Aaron Borger, who is the co-founder and CEO of Orbital Robotics, join us. He's done a lot of work in the space industry, working on robot arms that throw and catch balls on a NASA rocket at Blue Origin, and now he's working on some reinforcement learning on space, in space. And so please take it away. We're excited to hear what you have to say.
Yeah, thank you. Thanks for having me here, everyone. So I'm Aaron Borger. I'm the co-founder and CEO of Orbital Robotics, and we're a space logistics company working on capturing spacecraft with AI-controlled robotic arms, figuring out where those spacecraft are and how we can refuel, repair, deorbit space debris, and so on. So I started some of this work in my undergrad days where we had robotic arms on suborbital rockets that could throw and catch objects like a ball, a cube, a wrench. I worked at Blue Origin for a while and then worked on a PhD focused on satellite servicing. So some of the long-term vision, we want to put humans off the Earth and move them to the moon, Mars, orbiting space stations. But some of the first steps for this is we need robots. We need a whole bunch of robots that can build this infrastructure first on the moon, building large space stations in orbit. And all of you are working on some of the hardest problems of that here on the ground. It's just slightly different in orbit because you have to verify that no matter what happens, it will happen. It's much more safety critical. So this is some of the longer term vision. Where we're starting to do that is we are developing robotic arms that we manufacture that are space grade, and then we can sell to any company that has a spacecraft and wants to go and capture, deorbit some space debris or fix another spacecraft. And along with that, we include the software so that they can figure out where the spacecraft is, maneuver the robotic arms to go and grab it. So some of the work that I started off doing is I did the software for this payload, which was on a suborbital rocket, and we're testing RF signals in space. So this was my sophomore year in my undergrad days. It was a great project to get started. After that, worked on some robotic arms that could deploy from this system. These kind of 3D printed pieces show where the edges of the rocket are. There's another image I'll show you that shows them on the rocket. But the idea is you grab a ball, pull it out, throw it so the other arm can grab it. Some of the difficulties with this, it's a very small payload, so we had to manually build our own robotic arms, which also, as an undergrad student, we were taking 22 credits. I was also a track student, and so a lot of this is done just in the evenings, and we had 1 year to do it. So definitely a lot of progress just for that little time. But along with this, what we were able to do is figure out how do we catch the objects using deep reinforcement learning. So this is one example. And it actually worked on the first try, so I was really excited about that. And then this is more from the camera's view. And so we use computer vision to figure out where the object is, and then how we can capture it. And this is all trained in simulation using deep reinforcement learning. That's the video on the right. So you'll see it tries a whole bunch of times, and it fails sometimes. That's part of the issue with using deep reinforcement learning is it's hard to get it perfect 100% of the time. And you can also see this is it on the rocket right there. And so this was before it launched into space. But a lot of what I learned from this project is just figuring out, okay, deep reinforcement learning is hard to get it 100% of the time. And knowing from some of my work at Blue Origin, I worked on some AI machine learning for how you can predict the health of rocket engine components just from taking in temperature and pressure sensor readings. But people didn't really want to trust that because we're using a neural network, and a lot of the space industry, they really care about getting it 100% of the time. You can't, it works 95% of the time. That doesn't really matter when you're dealing with multi-million-dollar assets where that 5% of the time makes a huge difference. So since then, I've been focused on how do we guarantee that we can use neural networks and make it work 100% of the time, fully deterministic, not stochastic. There's another big problem that this video doesn't account for. That we call it dynamic coupling. So when you move the robotic arms, your spacecraft moves as well. And so that's fairly difficult if you go to try and grab something just using traditional inverse kinematics and your spacecraft moves out of the way. So some of the ways that we've been working on solving this, we can basically learn some of the difference between just a traditional inverse kinematics Jacobian, which relates the end effector velocity to each of the joint velocities, and then account for the spacecraft moving in response to that. And so this is what this demonstration is showing, is we can actually provide a velocity command on the end effector and go and grab the cube from that. From there, we can fully automate that and do more of a motion planning, trajectory optimization, while also learning some of the inverse kinematics. The other difficult part of this is a lot of this is in simulation, but in the real world, we may not know the exact inertial parameters of each of the links of the robotic arm. The joint dynamics are not entirely perfect. The contact dynamics aren't entirely perfect. So we also have to account for that. The time to real problem. Some of the ways that we're doing that is we can actually train in simulation and then using entirely physics-based models so we fully understand the dynamics of it, launch it into space, move the robotic arms around a little bit, and then go and grab some objects, and then focus on learning the difference between the data we gather on orbit and our physics equations that we use for training. That allows us to use a lot less data compared to if you try to fully learn the entire dynamics just from data gathered on orbit. And so this video is also demonstrating some of that, is we add a bunch of noise to the equations, the dynamic equations that we use for training, and then we see if we can kind of learn to adjust in simulation. The other piece of this, all these videos are showing static cubes, they're static spacecraft, but in reality, they're moving around a lot. So the next problem that we have to solve is the orbital mechanics. So if you have one spacecraft in orbit and then another spacecraft, if you're higher in orbit relative to this spacecraft, you're actually moving slower. If you're lower in orbit relative to this spacecraft, you're moving faster. And so we have to account for that as well. This is demonstrating some of that. And actually, all of these spacecraft is a Monte Carlo simulation. So all these spacecraft are controlled by the same neural network. They're focused on the blue arrow is like a solar array, the direction of the solar array. So we need to point that at the sun. Well, the green cone is a camera. And so we're trying to point it at this other cube, while at the same time making sure we don't go within like 100 meters of the other cube. And so there's a lot of different optimization problems we all have to do at the same time. And one interesting piece of this is controlled by a neural network, and we can actually verify that every single one of these scenarios, as long as it starts within a certain state space, we can prove that it will converge on some desired behavior, which in this case is pointing solar arrays at the sun, pointing the camera at the other spacecraft, and then remaining within some state safe region away. We can also apply this technology to a multi-agent problem. So this is an inspection of another spacecraft. The kind of blue circles are uninspected locations on the spacecraft. The green dots are inspected locations. And so we can coordinate between all these different spacecraft to do the inspection. This is also controlled by neural networks. And we can show that we can minimize the delta V used, the fuel usage, to still perform the inspection. Then the next question is, what happens when you add robotic arms to this? And so this is showing the same technology, trying to move the end effectors to a desired location while accounting for the dynamic coupling. So it's hard to see, but we...
Yep. The previous slide, I know you're like going through these, and if you're going to go deeper into it, we can pause. But maybe explain a little bit about like how do you structure the reward? Like what is the goal of it? Is it
the reward in this case is a 100% inspection. So we want all of these dots to be green, to be inspected. But we also want to minimize delta V usage. And so that's what you see at the top.
Delta V is?
Delta V is like fuel usage. Yeah, because every spacecraft, you can only change your velocity a certain amount. And so that's the delta V.
Got it. And then when you have more spacecrafts, like you can generalize this to more spacecrafts.
Yep, exactly.
And here it's producing a joint policy for all three of those.
Yep, they all follow the same policy.
Oh wait, so it's just a single policy for each agent and they each follow the same policy?
Yep, they know the other location and velocity of the other spacecraft.
Oh,
that's it.
Interesting. So it's decoupled that way.
Yep.
So they're not coordinated, they just sort of like happen to know what the other one's doing.
Correct.
Interesting. How would it perform if you just jointly optimized all of them? Would they spread into like a pyramidal or like?
That's a good question. Yeah, I haven't tried that specifically, but yeah, it definitely is an area that we want to figure out more.
I see. and then you have sparse, well, how is the reward structure?
Every time step they receive a reward. Because one of the other interesting parts of this is if you provide a reward sparsely, it's harder to verify. Some of the verification that we focus on is Lyapunov based. So we want to show that as long as the reward gets, and actually we do more of a cost instead of a reward, but we want to show that we get closer and closer to this kind of stable area.
Cool.
Any other questions on this one?
And is this the dynamics of the spacecraft are fully controllable? Like they're not small-time locally controllable, but they're like fully globally controllable.
Correct. Yeah, we have RCS, so we can control the orientation of it, and then you also have a thruster.
Okay. Got it.
So assuming that these cubes here, just checking my understanding, they're independent, let's say robots orbiting an object. What if one cube, orange cube, loses connection to the other two? What happens there?
Yeah, that's another technology that we're developing, and it's basically, okay, so you lose connection. Can you, in a way, have a safety ellipse, is what they call it. So you want to make sure that if you ever lose control, you're always on a trajectory that doesn't collide with the other spacecraft or the spacecraft that you're inspecting.
I guess like one of the advantages, if I understand correctly, of a decentralized control policy that you have is that if one of them were to stop working, the other two would continue to like cover. Right? Because all they know is the state of the other one, and the global coverage, right? Like they have some oracular access to global coverage.
And also this would be useful for, let's say, a spacecraft that is trying to maneuver away from your spacecraft. Then you can predict where it's going to move and always have one of your spacecraft in a location where it can continue the inspection.
I see. And then how does it generalize to like other shapes, like concavities and like things like that?
Yeah, so this one is mostly the sphere is focused on further away from the object. We just want to point our camera at every point on the spacecraft, for example, but really the shape of the spacecraft could be entirely different. So it probably has solar arrays, and so as long as we can go around like the entire sphere, then you should be able to look at every point on the spacecraft.
I see. Okay.
But then the next aspect is when we put robotic arms on, we also want to make sure that we can control them and account for this dynamic coupling. So we have control of the ADCS. We can control the attitude of the spacecraft. As you can see, we need to apply a torque to cancel out the robotic arms moving. And so this is also controlled by just one single neural network. We have custom simulation that can account for the basically conservation of momentum, which is when the robotic arms move, the spacecraft moves as well. And so we can control each robotic arm to a desired location. And then we can also do Monte Carlo simulations of this. So we want to verify that when a robotic arm starts in any random location, all the joints are completely randomized, that we can end up converging on a desired location. So all of these robotic arms are trying to move to this point. All of those robotic arms are trying to move to that point. We don't have collision avoidance on this yet, but we're working on adding that in as well.
Can I ask a very stupid?
Yeah.
How is it moving forward?
So we start with an initial velocity because you never really have zero velocity relative to the other spacecraft. And I guess the interesting piece of this is these are actually moving at 1,000 miles per hour around the Earth. But it's similar to when you're in a car. You don't realize all the other cars are moving at 90, 80 miles per hour as well. It's all about the relative velocity.
Yeah, because I guess like if you're conserving momentum, then your center of mass doesn't move unless you have like some external source of like falling cat and all that. Right?
Yeah.
So here you have some initial velocity. Got it.
Yeah, some initial velocity, and then we also have control over thrust. So we have thruster, 6 degree of freedom thrusters.
And you have a thruster on that one
also.
Yeah. I see. And it's on the red cube?
Yep. The red cube would be our spacecraft with the thrusters. Yep.
Got it.
How are you determining velocity compared to other objects around you? Are you using vision or?
Yes, that's a good question. I'll get to in like 2 slides.
Okay. Well, can I just ask one?
Yeah.
So, like, you're talking about mitigating the effects of the arms moving.
Yep.
You exploit it at all?
Yes. In fact, because most of the spacecraft that we're going to try to capture, let's say it's space debris, they're going to be tumbling. And so we want to find a way that we can capture the spacecraft, and likely we can move one robotic arm, move it quickly enough that we can cause our spacecraft to start to rotate, match that tumble speed, and then go on and capture it. Because also we want to find a kind of do a grasp generation that once we secure the grasp, it'll be easy to detumble. So yes, we're working on that as well. And a lot of this has been in simulation, but we actually have our own robotic arm. We actually put this together like 2 weeks ago. So we just have basic joint trajectory control, and this is our terrestrial version. But we have the space grade version of this. It's this robotic arm here, and we're going to be launching this first part of 2027. And so it's going to be on a spacecraft, maneuvering around, and doing a basic pick and place task. But building a robotic arm for space is pretty different from what you would build here on Earth, because here on Earth, you don't have to worry about a whole bunch of thermal constraints, you don't have radiation, and a lot of that is what we have to worry about. So part of it, we have processors in every joint. We also have a Jetson on board of this, an NVIDIA Jetson, so that we can use our AI vision processing as well as our neural network execution.
Hardened all of your, like Jetson, for example, to deal with radiation and other?
A lot of it is, so some of the other processors we have as well, they're automotive grade. And so you get single event upsets, basically radiation. You have to detect either a bit flip through ECC, or we can have radiation hardened memory on board and then periodically store data to that. And so if you reset, you can gather it. The other aspect is when we're doing our trajectory optimization and motion planning, we need to plan it such that at any point, if we lose control of it, because our controllers are resetting, that we aren't on a collision course. So it's almost saying we aren't going to make it radiation proof because there are processors like that exist, but they're $200,000, so it's not affordable for anyone who wants to do it commercially.
And anything for the motors and the other electronics?
The motors, for the most part, you can buy space grade versions as long as you get the temperature so that it's not like, it doesn't need to be a perfect temperature. You can get heaters for them. The other aspect is them getting too hot. That's kind of some of the issues that we're working through right now. But then you asked about the vision. How do you know where the other object is? And so I'll talk about that now. So this, one sec. There we go. So we want to use segmentation in a way that we don't have to train on objects, mostly because getting images of objects in space is very expensive. And you don't want to gather objects of the specific spacecraft that you want to capture or specific components of the spacecraft. The other aspect, like some methods use CAD models of these specific spacecraft and then try to generate 3D point clouds and match that to the spacecraft. We don't want to use that. So we use like a few-shot learning approach where you only need the first frame of the video and you can track that. You can actually get that from a thermal camera pretty easily. So we have thermal cameras on board in serial, so we can triangulate and get the depth estimation. But then this few-shot learning, you can use a combination of CNNs and attention mechanisms to compare this first frame to all the other frames in the video. And so we can count for occlusions, we can account for different lighting variations. And we've actually tested this on some footage from space. So this was from a couple years ago. You'll see a capsule come out here shortly. And we haven't trained on this capsule. We don't have any CAD models of it. And this neural network was trained on objects entirely from Earth. And so this is the first time it's seen things from space, which is, in a lot of the literature, they argue it's out of distribution for things in space, but we're able to show that it clearly isn't. So we just need an initial indication of where the object is, and then we can continue tracking it anyways. Yeah?
How do you give it that initial indication? Like there could be a bunch of things in the scene. How do they know that's the thing to track?
In this demonstration, we have someone that says, track here. But in reality, we have a thermal camera. And you can, let's say you're further away. As long as you're pointing away from the Earth, the spacecraft's going to be the only thing that has heat compared to the background.
follow up on that, why not just use thermal then? Like wouldn't thermal directly give you the segment?
Yes, but then we also want to figure out what the orientation is. So then you want to figure out, okay, this point on the spacecraft, you can start doing like SLAM-based methods where you say, okay, this point on the spacecraft now rotates here, and then we can do an initial 6 degree of freedom pose estimation from that.
What if the object takes up your entire FOV?
Then we want to start tracking specific components on the object instead, which there's a couple other few-shot learning methods we could use, or we say, okay, I want to train it to track all screws, something like that, or maybe it's a docking port, and we can train it to detect specific locations on the docking port.
Do you have any issues when objects come that's begin in the frame, exit the frame, and then come back?
No, I think, does this video show that? Maybe. I think this video shows you can like hide it and then it comes back. It's mostly because you're only comparing the current frame to all the previous frames. So it's more figuring out this is what the object looks like. And then later on, I see, hey, that object appears again in these pixels.
Do you use any sort of admittance controllers or something? Because, like, let's say you didn't have a successful grasp of your object, and it just held on. The arm could shear off from the main body because of just the force of the ball. So do you have, like, it slowly latches on. If it doesn't make a good grasp, then it just sort of backs off and tries a second run or a third run again.
Yeah. Did you say, do we have any admittance controllers? Yeah, we're adding force torque sensors to the end effector so we can start to figure out, okay, you have maybe touched it here, now you can adjust, and working on the policies to control that as well, so yeah.
So are you trying to train a very general policy able to grasp almost anything, or are there specific objects, materials, things that you're trying to grasp?
I would say we want to stay away from general foundation models, for example. We want to stay away from the general policies because we want to verify it for a very specific mission. So for example, people are going to spend $50 million, and that's actually a price that the government has paid companies to perform a service on a spacecraft. So they're going to spend that much. We are going to focus on developing a model for each specific mission and tailor it to that. So this is one example of a spacecraft that we're developing. We have robotic arms on it, and then this is actually, this piece here is designed to connect to the Hubble telescope. So the Hubble was put up a while ago, and there's been a couple astronauts who have gone up and serviced it in person, but it's actually coming to re-enter the Earth's atmosphere in 2030, 2031 is when it's estimated, but we need to catch it before that because we need more delta V. Because if you wait until it's like 200, 100 kilometers, it takes more fuel to boost it. So like 2027, 2028 timeframe, we would take this spacecraft, go up to the Hubble telescope, mount these parts on it. That's a star tracker there. So star trackers figure out the attitude, the orientation of the telescope. It has broken rate sensing units, which is basically how it figures out how fast it's spinning. And so we can replace it with these star trackers. And we've actually been working with a couple of astronauts who went up there and serviced it, and NASA, and trying to convince them that we need to save the Hubble telescope, in part because there's actually a 1 in 240 chance that when it comes down into Earth, not all of the components will burn up in the atmosphere. So when those hit the ground, there's a 1 in 240 chance that there's a catastrophe. So we're working on capturing it, and this is a simulation example. We can grab this, maybe the lighting's a little off, but this ring here is called the soft capture ring, and you can go up, capture it with robotic arms, and then pull the spacecraft in, and then boost it.
So if you boost it, will it have a longer service life?
Yeah, they estimated if we boost it, it'd last 15 to 20 more years. And there's still a ton of science that needs to be done on the telescope.
So do you detach that payload? Like, I guess we'll see it in this video.
So we grab it with, this video was kind of before we came up with this model. Let me go up. this model. But yeah, we grab it with our robotic arms, pull ourselves in, boost it, and then leave this payload behind on that soft capture ring. There's clips on this that can clip and grasp onto that ring, and then we detach from it, basically detach here.
And that has thrusters.
This spacecraft has thrusters. The Hubble doesn't have thrusters, which is partially why we need to boost it.
I see. Got it.
That little tiny thing has enough fuel and everything?
Yep. Yeah.
Question. So when you say you like grab onto the Hubble and then you pull it in, is there like a docking mechanism that happens, or are you relying on the arms to hold
So
it?
part of the reason why this is so complicated is there is a docking component. That's that soft capture mechanism. It was the predecessor to what's on the ISS right now, but currently there's no other side to it because it was built so long ago. So that's partially why the robotic arms go up, because SpaceX was actually looking at doing a similar mission to this, but they would have humans on their Dragon spacecraft. And then they decided that having humans on the spacecraft that would go up and service it would be too costly for what they wanted to do.
So related question is, like, the real question was, when you do attach to it, it's like a rigid connection.
Yep.
Right, okay.
Yeah.
When you go up to grasp that specific ring, are you attaching yourself throughout the rest of the cycle? And you are kind of like a backpack, and then when it comes back again, you can boost again? Or?
The goal is that we would boost it and then let go, in part because our fuel on board this spacecraft and our robotic arms add dynamics to it. And they have very precise pointing, so they can point at stars super far away. And so we would mess up the dynamics and basically make it much more harder to point the telescope. So we need to release, and then our spacecraft can go service another spacecraft. Yeah.
So do you expect to have perfect models for simulation of basically anything you're going to service, or do you also have to think about generalizing to new types of grasps and objects?
Yeah, it depends on these spacecraft. A lot of them have what's called a launch adapter ring, which is the interface that it needs to connect with the rocket on launch. And so all of them have that same interface. As long as we can develop an end effector that can grasp onto that, then we shouldn't need to generalize to basically any shape to grab. But some of those may be different sized, slightly different geometry, or degraded. And so we do need to still figure out where on this launch adapter ring do we need to grab. It also could be tumbling at different rates. And so we need to figure out, okay, based on its tumble rate, what way do we want to grab it? But yeah, so we don't assume perfect CAD models. We also don't assume perfect, basically, dynamic models of our spacecraft. And we also need to perform some system identification of the spacecraft that we're trying to capture, because we won't know its inertial parameters. And then if you try to capture it and it's more heavier than you thought, or its mass is distributed differently in the spacecraft, then that could mess up your grappling as well.
I'm assuming.
But I had a. You can go first.
I'm assuming that you put this package into a rocket. Do you make your rockets, or do you rely on a different company?
We'll mostly rely on SpaceX, Blue Origin. There's even Rocket Lab and Stoke are coming up. So yeah, definitely relying on other companies for that.
So it's the question, I guess, related to the risk side of it, which is, you suppose like you take a contract for some servicing a satellite, and then even if it's done by a human, like the job can go haywire. What's like the downside that does that come to you? Like, is just like curious about that.
Yeah, there's a lot of regulation issues about this whole satellite servicing that haven't been solved yet, and that's one of them. Is no one's really sure if, okay, you're trying to service this other satellite, what happens if it goes wrong? There's definitely some liability issues that need to be solved there, but that's also why we're so focused on, we need to guarantee it will work 100% of the time and go through every scenario. Okay, if this happens, what do we do? And have degraded performance. So let's say one of our components fails. How can we still complete the mission even though that component has failed?
That's actually the great thing about being a startup is you can take that risk.
Yeah.
And if you lose, you lose. But a big company is going to be worried about the downside for their existing business.
Yeah. There's also big companies who are working on this as well. But they're also focused on government contracts with very expensive spacecraft, which they can kind of get away with. And that's also an area where I guess you need to ask the question, do you need to use AI and reinforcement learning and all this? They don't, because they have very large spacecraft, and the mass of the spacecraft is large relative to the robotic arms. So if you have very small robotic arms and you move them around, your spacecraft doesn't move that much, your attitude control system can account for that. But if you want to make it lower cost and actually commercially viable for smaller companies, then when you move your robotic arms around, you want less spacecraft mass, but then your spacecraft's going to move around. And that's why we need to use the AI, is so we can get away with using less mass and predict how it's going to move.
Another question about, so when you are moving one arm to like compensate for the motion of the other, have you guys done the math on like, is it cost effective to do this versus say using a combination of this with RCS? Because you could just use RCS as well to compensate for the momentum, right?
Yeah. So I think there's a couple different methods that you could do. One is you just use normal control, like traditional control algorithms, inverse kinematics, to go and capture it, and then assume that your ADCS can stabilize your base and keep it still. That works if you have a very large spacecraft compared to your robotic arms. Once you try to do a much smaller spacecraft, you can't size the ADCS appropriately to account for that. So then, yeah, I think that mostly answers it. Is yes, it works if it's large.
But your arms are electric and running off of solar that you can harvest again, right?
Yeah.
And your RCS is all. When it's gone, it's gone.
Yeah, and there is some, so you can have reaction wheels or control moment gyros that are just spinning, and it's basically, that's also electric, but there is some like RCS where you have thrusters that you thrust to spin it, and that is a finite resource. But that's also why we need to develop this tech to go and capture other spacecraft, is so that we can refuel them instead of treating it as a finite resource.
So you talked about like replacing a processor board. I guess that was on the Hubble.
Yeah.
It's designed.
Hubble or any other spacecraft. There's a lot of them that it needs to be done to.
But have they've been designed to...
No. They have not been designed to accommodate new upgrades or even repairing. All the spacecraft in orbit, they're just starting to say, hey, maybe we should design this so it's easier to repair. Right now, all of them are not designed for that. So a lot of it you'd have to communicate with RF, the new processor that you attach. It need its own power source. But even with all those complications, it's worthwhile compared to using the old processor.
So you think you don't have to remove the old one, you can just slap a thing on and communicates well. Oh, I see.
Yep.
That sounds more feasible.
You speak with satellite manufacturers. Have you noticed any changes in the way they build satellites to maybe make them more service-friendly or modular in some capacity, or is that something you're trying to sell to them?
There's a lot of companies, OrbitFab is an example, where they are building refueling interfaces that you can put on spacecraft. The issue is you're going to put that on a new spacecraft that launches today, and then you have to wait 10, 15 years before you'd even service it. So all the spacecraft up there, there's thousands of them right now that aren't prepared. So we're addressing the problem that needs to be done today, basically, instead of waiting 15 years or so for some of those interfaces to be able to be useful. That's what I had prepared, but yeah.
Okay, then question I had, going back to many slides. When you had like the policies doing as like globe coverage, or even like the one before that, you mentioned like you had done some sort of validation to verify that policies were always going to work within certain bounds. How do you do that verification?
A lot of that I can't go into too much because it's just company IP, but Lyapunov stability is what it's based off of. So in Lyapunov stability is, let's say you have some system, you have an energy-based function or value function. Let's say, for example, you have one object here, you have another object. You want to move this object to here. And it starts in some state space here, somewhere in this distribution. As long as you can verify that it gets closer and closer over time, it will eventually reach there. Even if it starts from over here, it will get closer and closer. But then you can also verify that if it gets closer at faster than some rate, asymptotic stability, then it will reach there faster than some amount of time. And if it exponentially gets closer and closer, you can verify it'll get there even faster. So that's what it's based off of.
You said policies, and I guess probably most people when they think of policy, they mean like you're just directly predicting actions. It sounds like your policies, you're more structuring it. Maybe you're learning some definite function or some barrier function. Like there's like some stuff under the hood.
The policy is neural network based.
Yeah, but it's not like just directly spitting out an action. There's like more structure to how you're formulating it.
Slightly. I mean, we do take in an observation, spit out an action, and then we need to check the action to make sure, one, it's within limits that are physically capable, and then also that, let's say, even though we've trained it to come up, capture it, if it's moving in too fast and then it says we want to thrust even more towards the other spacecraft, we should check that and say, that doesn't make sense, that's probably not safe. And so there are some additional checks that we need to do.
But if you do them and there's no more actions left, then I guess your policy is no longer valid, right? You need to make sure that you have enough valid actions such that one of them, even though it's a stochastic policy, one of them will have to satisfy your constraints, and you need to be able to find it.
Yeah, and we do also want to make sure we don't use stochastic policies. We focus on deterministic policies. So we don't add like randomization to actions. We provide inputs and then directly take the output.
I see. And if one of them doesn't satisfy the constraint, then what do you end up doing?
A lot of it is we want to have kind of backup policies. So, okay, we're coming in, for some reason we're moving too fast. Then we have another policy that says, okay, slow down if you're moving in too fast. If that doesn't work, then we do need to rely on some traditional control methods, but those can be much simpler. We no longer have to capture the spacecraft. At that point, we're just point away and thrust.
Yeah. When you say you're only training deterministic policies, is that also during training time, or do you mean only for evaluation?
During training time as well. Yeah.
How do you explore?
The exploration is based on randomizing the kind of state space that we start at.
I see. So the policy node has to explore, at
least
in the way that you're training.
Yeah, and I guess, so the policy itself is deterministic, but we can still add noise to actions on the output to explore, okay, what if it's slightly different output?
Yeah. So you said you do reinforcement learning because MPC is too slow. But you could just do MPC, generate a bunch of trajectories, and do supervised learning. Why not do that? Like you just generate a bunch of data and do supervised learning. Like RL is kind of a pain in the ass, right? So like you should avoid RL when you can avoid RL.
Take it from
so, you know, like I wonder why that's not the strategy that you would adopt.
Well, I would say partially if you're trying to use MPC for robotic arms on the spacecraft, you have to calculate how the robotic arms affect the spacecraft, but then also the contact dynamics. And
but it's a simulator. Like just do sampling-based MPC or something. Like, well, like you don't have to do anything beyond this. The simulator is doing everything for you, right?
Yeah, I think in part also I'm thinking when you're moving in with your spacecraft, coming in and trying to capture it, you want to know beforehand what it will do instead of trying to figure out, okay, is it going to optimize it slightly different than what we've seen in the past? And I know a lot of the rocket landings, for example, they use MPC. So
there's MPC at test time, but like you're in a simulator and you're doing RL in the simulator, right?
Yeah.
But you could do MPC at training time, and if you have like a reward function that's reasonably informative, like MPC works really well. Maybe think.
Yeah, that's a good point.
Abhishek, is that technique used commonly, like learn MPC?
Some people do. Like generate data with MPC and then imitate it.
I think maybe the question there is how do you prove that it will work? 100% of the time.
The same way that you prove things with your reinforcement learning controller, right? Like you could use the same Lyapunov stability for your learned controllers.
Okay.
So is the point in knowing how you're going to grasp, or what's going to happen when you grasp this object in space? For example, if you go up and grasp it and you determine it's rotating at this velocity, you can know how much force you have to apply to inverse that velocity or that spin. Is that one use case of that?
Yeah, and partially we want to do grasp generation such that we can easily detumble it. So we don't want to do like a grasp where our arms are super close together like this, because then it's hard to detumble the spacecraft.
How are you defining detumbling? Is that in what axis?
It's in all axis, the angular velocity is minimized to 0, or very close to it.
Yeah. So you said you have to do some like system identification, and you maybe hinted that you're learning some additional corrections to your simulator, or is it that you're just learning what physical parameters are correct? Are you doing some additional learned world model on top of your simulator?
Yeah, and a lot of it is probably more simplistic than what you would do on Earth. So you could either learn a polynomial or like a matrix that you can apply to the already like physics-based model that you have. So for example, you have an inertial parameter matrix that may not be completely accurate or completely precise. So you can learn another matrix that you multiply them together, and then after they're multiplied together, the final matrix is much more accurate. So a couple methods like that.
Is there a benefit to that over just learning the parameters to begin with?
Less data, for the most part. Because if you already have an idea of what the physics are, then after you launch it and try to move it around, gather data, then you don't need to learn it from scratch, which requires more data.
Any more questions?
Okay, now let's thank Aaron again.
Yeah, thanks for having me.